Good morning. My name is Matt Wright, and today I'm here to talk to you about the last method for determining the potential or the electric field. We are going to look at the dipole expansion or the multipole expansion. So this is kind of like the last hurrah. So let's recap what we've done so far. We've done Coulomb's law. So you can find it using the electric field in Coulomb's law, or you can find it with the potential. We also talked about the possibility of using Gauss's law. While Gauss's law is always true, we proved that, it's only useful in certain situations, and that'll tell me the E field directly. We talked about numerically finding the potential by solving the Laplace equation. We solved electric potential problems by creating this weird image charge, and we were able to look at the method of images. And we were able to solve the Laplace equation directly as a differential equation. Now we're going to look at the final technique. We're going to look at expansion. Okay, so let's start with a simple problem. Imagine that I have two charges, Q1 and Q2, right? And I set it up so that Q1 is equal to minus Q2. Okay, they're both along the y-axis. This distance is A. This distance is A. Okay, and this distance here is D. That's the distance between the two. Now I want to find the electric potential. So what I'm going to do, well, specifically I want to find the electric potential at some point P, right, which is some distance away from those two charges. Well, in order to find this, I have to figure out what script R is. Okay. So here is script R1, and here is script R2. So I can write down the potential in terms of script R1 and script R2, right? Using the principle of superposition. So V is equal to V1 plus V2, right? And so V is equal to 1 over 4 pi epsilon naught Q1 over script R1 plus 1 over 4 pi epsilon naught Q2 over script R2. So I can pull out what I already know is the same on both terms. Q1 over 4 pi epsilon naught 1 over script R1 minus 1 over script R2. Right, remember that the charges for this example problem here, the charges are the same in magnitude but different in sign. Right, so I can pull out the Q, but when I do, I get a minus sign. So we're just going to go ahead and call Q1 equal to Q, and we're not even going to think about whether or not we're just going to lose the 1 in the derivation, make our lives a little bit easier. And so the question is what the crap is script R1 and what the crap is script R2? And so that becomes kind of like the mission of the problem, right? So, well, if I look at what script R1 is, well, I'm going to go ahead and define this as the distance r, right? And so if I want to figure out what to do, well, I'm going to go ahead and write down now, using the law of cosines, script r1 squared is equal to r squared plus a squared minus 2ra cosine of theta, where theta is now this angle here, right? So what I'm doing here is I'm just writing down the law of cosines, right? A squared plus r squared minus 2ra cosine of the angle is equal to script r1 squared. Again, law of cosines. Okay, and what would script r2 be? Well, script r2 squared, well, you're still going to have an r there. Your angle now is going to be this angle right here, right? So you're going to have r squared and plus a squared minus 2ra cosine phi. Have that angle there, the cosine phi angle. All right, so that's interesting, right? So I have this cosine theta and this cosine phi. How are they going to be related? And that's going to be the big question. So what we want to do is let's think about theta and phi. So theta plus phi equals pi, right? If I go here to there, I go 180 degrees, right? So if I add the theta and the phi together, I get pi. Okay, so the cosine of phi is going to be equal to the cosine of pi minus theta. And then I can use an identity that tells me that this is going to be minus the cosine of theta. So how might I prove that? Well, let's just use the Euler's law. You get pi e to the minus I theta plus e to the minus I pi e to the plus I theta divided by 2, right? What's e to the I pi? E to the I pi is going to be, well, e to the 0 is 1, e to the I pi over 2 is I, so e to the I pi is going to be minus 1. So this becomes minus 1 e to the minus I theta plus now a minus 1 here, e to the I theta divided by 2. You pull out the minus 1 and you get minus 1/2 e to the I theta plus e to the minus I theta, right? Which is, of course, the cosine, or minus cosine theta. So that allows me to rewrite this equation, right? Because in this equation I have phi. So if I do script r squared, script r2 squared, r squared plus a squared. And now if I plug in for the theta, it's plus 2ra cosine theta. Again, what I did was I found the relationship between theta and phi, and I thought about how the cosine of phi is actually equal to minus the cosine of theta, because theta and phi are related. And then what I did was I just plugged that in here to this relationship. It turns that to a positive. But that's super, 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 super important. Okay, so now we're gonna do something pretty neat. We're gonna go ahead and pull out an r squared here. So that script r1 becomes script r1 squared becomes r squared 1 plus a squared over r squared minus 2 a over r cosine theta. And if we do the same thing, and for script r2, we get r squared 1 plus a squared over r squared, now plus 2a over r cosine theta. So what I essentially did was I went ahead and I pulled out the r squared from each of these terms, right? And now I can take these values for script r and I can plug it into my equation for my potential. It starts looking ugly, but here we go. Q over 4 pi r epsilon naught, right? Because this is script r1 and this is script r1 squared. So when I take the square root, right? And then I have over the square root of 1 plus a squared over r squared minus 2a over r cosine theta minus okay. And now I get something, right? I've factored out the r in both terms, right? And now I get something that I can start to play around with. All right, so I'm going to go ahead and make an approximation. I'm going to say that this point P is so far away from these charges that the quantity A over R is maybe not 0, but a squared over r squared is approximately 0. So this is pretty far away. It's far enough that you can kind of make out that there's two charges and not just one, but it's pretty far away, such that a squared over r squared is 0. So when I do that, it's going to go ahead and simplify the following equation for the potential. Every term that is a squared over r squared, I'm just going to make it go to 0 here. So you get q over 4 pi epsilon naught r, 1 over the square root of 1 minus 2a over r cosine theta minus 1 over 1 plus 2a over r cosine theta. All right, now we know that this term is small, right? Because a over r is going to be small, right? We know that a squared over r squared is really small. It's so small we're going to consider it 0. But we also know that 1 over a is going to be small. So we want to look at this term and maybe we'll do an expansion. So we are going to consider the following. 1 over the square root of 1 minus x. And we are going to expand that, okay? So we're going to do a Taylor expansion. Okay, so the first thing is f of 0 is going to be, well, if I plug in 0 here, it amounts to 1. Okay? Now if I do f prime of x, I have to do the chain rule here. So minus 1/2, right? I'm going to take this derivative, so it's going to go down, minus x to the 3/2. And then, in the top, I'm going to get I have to do the chain rule, do that derivative there, I'm going to get a minus 1. So this becomes equal to 1/2 1 over x minus 1 over 1 minus x 3/2, right? And so then x of 0, or sorry, f prime of 0 is simply just going to be 1/2. All right, let's keep going. But wait a minute, should we? If I look at the expansion, right, the Taylor expansion is going to be f of x 0 plus x, f prime of 0 plus 1/2 x squared f double prime of 0, and so on, all the way out. Now, if I'm going to go ahead and call x 2a over r cosine theta, then anywhere I have an x squared, you're going to have 2 squared a squared over 4 squared cosine squared theta. There I have that ratio, a squared over r squared. So remember I said that anywhere I have that term, I'm going to go ahead and make that 0. So I'm only going to need to know the first two terms in this expansion. So f of x is going, for this f, is approximately going to be 1 minus 1/2 x. Now if I make this a positive x, if I want 1 over the square root of 1 plus x, I can just plug in a minus x here. So for the one term it's this, and for the two term it is 1 plus 1/2 x. So, right, because here I have 1 minus x, here I have 1 plus x. So when I put them in, I get the following. Right? So notice there's a 1/2 and there's a 2, so they're going to cancel. Right? And so now I just need to do some arithmetic here. This is approximate now. Well, it was approximate here too, once I got rid of the a squared over r squared term. Okay, so the potential now, it's going to reduce down to V equals Q over 4 pi epsilon naught R 1 minus A over R cosine theta. Right? Now I'm going to distribute this minus sign through. So minus, now a minus A over R cosine theta. Okay? Well, 1 minus 1, right? Ooh, me have 1 cookie and then me eat it. Oh, nom, 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 nom. How many cookies do I have left? Right? And if I knock that out, these terms are going to go away. Right? 1 minus 1 is 0, and I'm left with just these two terms. So V is equal to Q over 4 pi epsilon naught r squared times 2a cosine theta. And so this is the approximate potential when you're far away. Okay? Now, let's clean this up a little bit more. Okay, so 2a is d. So I have v is approximately qd cosine theta over 4 pi epsilon naught r squared. Well, if I look at qd and I say that d starts here and goes here to this charge, so from 1 to 2, or sorry, from here, from the bottom charge to the top charge, and I call that my vector, right? And I know that here is my point P, and my r hat points in that direction. I can define a vector, we'll call it little p, dipole moment, right? The little p is the dipole moment, and it's equal to q d, right? Where d is the direction of the dipole moment. So if I take that and I say qd dot r hat, right, would just give me that cosine of the theta between them. So this would become qd cosine theta. So I can really write my potential in the following way. So now what I have is I have a way to think about my potential. The first non-zero term in the expansion is a dipole, two charges, right? It goes, if you're far away, that's just 1 over r squared. And this is great, right? Because it tells us kind of how this potential behaves in a nice, closed analytical form. Okay, so this is part 1, and we'll move on to part 2 in a moment. I just want to make a quick comment before I do. We can always rewrite, just doing the same trick that we did before with the Q, right? So we have, this is really r prime cosine theta over 4 pi epsilon naught r squared. Make sure I didn't give a 2 in there, yeah, right? So, so if I want to do this for a object that's just not 2 points, but is more than 2 points, right, I can take my Q and I can rewrite it as a charge distribution. And when I do that, I can get this very cute equation here. Now I'm going to have this integral over the primes, and I can just take this dipole moment equation and I can think about it, keeping this same form in connecting these. I can take this and rewrite this as the dipole moment is simply equal to the integral of rho as a function of the prime coordinates times r prime vector, right, integrated d3 x prime. So this is saying, if I want to know what Q is, right, I integrate the charge density directly, right? And if I add up all the charges, charge density, I get the total charge. But to find the dipole, I have the next term in the expansion. I am multiplying it, the charge density, by the position of the objects and adding them up over the volume. And that'll tell me what the dipole moment is. So I don't have to use this more complicated equation. Once I find this, it's going to be a vector, right? I can take it and go ahead and plug it right into that equation. I know what my R hat is, and I can determine what the potential approximately is a long way away.